All right, so I just want to finish with my previous lecture. So these probabilities for selecting them, for selecting the rows, is beta is greater than beta ui, the i's row of u. You know, A is equal to u sigma v. I mean the SVD of that. This is n by row, this is diagonal, and this is row by row. This is right singular eigenvectors, and this is row by d. And so in the previous algorithm, you just know, of course, a row is the rank of A. So you just need to know that if your probability of selection is greater than this sum of all norm of all eigenvectors, then this is beta times your leverage score. So leverage score that is so popular is just these parts. This is called leverage score. So everything is related to SVD. And the order of ND squared suffices to compute probabilities and to construct a core set. And I want to say that, you know, all of these motivation was to somehow reduce the complexity of the kernel. So, but in kernel approximation can be done in several ways. Two of them, I just talk about two of them. The first one is Nystrom approximation, which approximates the kernel matrix, which was X transpose X that I talked in the previous lecture. And the second approach, which is driven by that Iranian guy, I forgot his name, random features, which is very, very popular and very mysterious. Still, people think that it is very mysterious, but it is just a property that we use in measure theory, that our measure is a probability measure, and we look at that function as a probability measure, and we can just sample that. But I will explain about random features. So, random features. You know, everything is about the Johnson-Lindenstrass lemma in Johnson-Lindenstrass, sometimes JL, they call it JL. In 1984, Johnson-Lindenstrass lemma. And two important articles which is written after that to develop these ideas of random features. It was first described in random kitchen sinks by that Iranian guy was Rahimi in Resht, NIPS 2008. Very simple and very important and very well cited article. And this article and this article are very important. Fast food, which is by Lee et al. In 2013. So why random projections? Because they're fast, efficient, and distance-preserving dimension reduction, the idea of JL, Johnson and Lindenstrass, those two mathematicians, was that you have, for example, the picture of Elon Musk here, the picture of me is here. For example, if the distance between them is delta, then in a probably lower dimensional space, their distance is just the same, but with epsilon error. And in this space, you have 1000 dimension is 1000, but this is the dimension of your original space, which is the number of pixels of your image, because it's number of features. And so the idea is that we want a matrix A, we want a matrix W to project them, and this matrix is in R by 1000. So this matrix lies in this. So R, so this W matrix allows us to write in the new space. We can write Y in the new space becomes this, and the only things is that it is possible to find such a function, and the important things is that it preserves the distances. So the distance between y and y2, so this is y1, this is y2, and this one's x1 Elon Musk, x2 me. So the distance is preserved, and it is between x1 squared, 1 minus epsilon, and 1 plus epsilon. x1 minus x2 squared. So this is random. This W is a random matrix. And it is sampled from a normal distribution, and it is fast. And all of these fast food, fast, everything fast comes from the fact that you can just simply draw as a matrix from a random matrix set. So this Johnson-Lindenstrass lemma was proved by Paul Erdős, which is a Hungarian mathematician, and worked on some everything: geometry, probability, graph theory, very importantly, graph theory. And there is the lemma says, JL lemma says that there exists, even exists of this one is important. There exists a linear map from Rn to Rn, such that this map preserve the distances. Exactly what I've written in the previous page. So this is 1 plus epsilon u minus v squared, and 1 minus epsilon u minus v squared. So if you're wasting too much time with principal component analysis, consider random projection, because it's very easy. You just draw a matrix, a random matrix, and that's it. So, especially if you have a huge feature matrix, you should consider random projection. So random kitchen sinks article is that you have a function f of x, I from 1 to t, alpha I phi x w I. You want to approximate that. This is a huge kernel matrix. So my lectures are all about scalability in machine learning. And one of their problem is that they have a huge kernel matrix, and each row, each point of this xi, xj, it is a huge matrix. For example, billion by billion matrix, which corresponds to a billion images, for example, or billion words, or billion assets. And you want to approximate this, so f of x is from I alpha I phi x wi, but we want to approximate it with only t of them. So ft of x is just t. Instead of infinite number of bases, you approximate it with very limited. So the greedy fitting is so you want both alpha and w, which is minimum. We want to minimize this approximation, which is a finite sum of phi, and f, which is an infinite sum with probability measure mu. And the intuition is that you have a circle, for example, you want to approximate it with some polytope. And so it all depends on, so in measure theory, if you have a background in measure theory, you get what I mean. So so we want to approximate kernels with RKS. And I want to start by Buchner Theorem, because the proof is just a simple usage of Buchner Theorem. A kernel kx minus 1 on Rd is positive semi-definite if and if kx minus y is a Fourier transform of a non-negative measure p. So in other words, kx minus 1, you can write some kernels as kx and y if they are shift invariant. And this is p of omega. This is consider this as a Fourier transform of your kernel, of kernel k of x and y. So p is just Fourier transform, but we consider it as a probability distribution. This is the trick. Times ej x minus y d omega. And because this is an integral, and so we just sample average it. So this is approximately I from 1 to t, but t is a design variable, so it's very important to know that how many finite sum do you need. And there is a minimum that you have to have, because otherwise you lose your information. J omega prime x minus y. So because you can write it as a product of two of them. This is the exponential function, and so you can write it as j y, and this is phi y w, and this is phi of x w. This is your features, and so it becomes so you can write it as phi x w phi y w. This was the idea of random features. Of course, there are two types of random features. This was the Fourier The other one is random binning features, which is less popular, but it's still important. All of them are related to measure theory, if somebody knows that measure theory. So in big data, you can, for example, I talk about kernel matrix. The old idea is that you use a kernel machine training and then use classifier. But the new approach is this: we use randomly featurize it. And then you have a linear machine training, and then you have classifier. So finally, you get your classifier. But the random features that I explained was about Fourier features. So don't forget that when I talk about random feature, it means two different things. Random Fourier features, which I proved that by Buchner lemma, and it is good for linear for learning global interactions, just like Fourier, that you write with sum of bases, and it shows you the global structure of that function space. And the second approach to random feature is that it is random binning feature, which is good for locality. I mean you leverage locality. And the idea of random binning is very simple. You just sample m vectors, and you put it in. For example, if this is y, this is the index of x, which is 12, index of y is 3. You can write it in a bitwise, of course. You see which of these blocks is related to that point. But I want to rewrite the algorithm for the Fourier features, for random Fourier features. I want to summarize that. We first sample m vectors, W1, W2, Wm, from P distribution. I said that this is the Fourier transform of your kernel. And after that, you generate random features for each sample. Sine of W1 transpose Xi, cosine of W1 transpose Xi, sine of W2 transpose Xi, cosine of W2 transpose Xi, sine of Wm transpose Xi, cosine of Wm transpose Xi. I told you that this m is a design variable. So the larger m, you get a better approximation. It's like the SVD that you approximate an image. The higher number of eigenvalues, the sub matrix that you use, you have a better approximation. Here as well. When m is large, you get better approximation. If m is too low, you may suddenly lose your informations, and you may not get what the information inside the matrix. So it should be a trade-off between very low m and very large m. And the time and finally